All right, hello everybody, and welcome to your favorite videos on the internet, math videos. Okay, so today we are doing some new stuff. I think it's exciting. I don't think most people have seen this in this class before, so it's new, which sometimes it's always nice to learn new stuff because then you're like, oh, I know about blah blah blah. I'm so fancy. So anyways, that's what we're doing today. So we are starting our vectors piece of this applied trigonometry unit. So we're going to figure out what is a vector. We're going to learn how to label and name vectors. We're going to talk about magnitude and direction, and then we're going to do some examples of how to find magnitude and direction of vectors. So pretty easy day. The math we're going to do today is not complicated, but it's probably going to be a longer video because we do have to go into the details of vectors a little bit because it's like our first day, right? So here we go. Okay. All right. So I know this is like a lot of stuff up here, but this is referring to our warm-up problem. So the warm-up problem we did today where we had someone walking, along a path in a certain direction, like for a length and in a direction, that is called a displacement. All right, because it represents the shortest distance from initial point to a final point. All right, and so what we're doing in that problem, which I know it doesn't seem that complicated, but we're giving a numeric value to both the distance and direction a person traveled. And anytime you're measuring multiple things at once, you need a new way to kind of represent that data. So because of these two different measurements, right? So we have, like I said, we have direction and we have length that we're traveling. We are, that's basically what vectors do is they help us represent these two quantities at one time. All right, so instead of having a point and an angle, right, like we do with our unit circle, right, we have a point and the angle. All right, we're going to merge those into one piece so that you don't have to keep track of both. All right, and this is what vectors do, so it's kind of nice. So it's giving us a way to, like I said, represent direction and angle with just one piece instead of having two separate pieces. All right, so we will just get started. Hold on. Okay, so sorry, I like lost something and I had to find it. Okay. All right. So let's just highlight this. So I know this is a lot of stuff, and I definitely wouldn't say write all of this down. All right. All right, so this is basically what you need to remember. So vectors give a numeric value to both distance and direction. All right, so that's like the main takeaway there. All right, and this is what vectors do. All right, so they give a single value, one numeric value to both distance and direction. All right, so you don't have to keep an angle separate from the coordinate point. We're actually going to merge them. All right, so a vector, here is its textbook definition. It's a directed line segment. So it's not really that cool. It's a directed line segment. All right, so hopefully bringing back some geometry. All right, a segment has a distinct start and a distinct stop. All right, so since we have a start and a stop, because we are a segment, that means we have length. We can measure the length of a vector. All right, so uh, they can be measured. So they can be measured. All right, meaning they have length. All right, so we'll just do slash. What can you see? Okay, they have length. Now we call this length the magnitude. All right, so it's just a vocab word. It's nothing scary. All right, but the length of our vector, we call this the magnitude of our vector. All right, so the length, we call this the magnitude. All right, now when you get into more advanced vector mathematics, which is not going to be in this course. We're just doing the basic intro level stuff. You're going to see magnitude or length represented by other words such as velocity or speed. We do a couple word problems, but it's nothing too crazy. But if you see those words when you're dealing with vectors, all right, you see like the speed of something or the velocity of something, it's referring to the magnitude of the vector. It's, we're going 25 miles per hour. Well, that's a speed, but it's also a length. You're going 25 miles, that's a distance. All right, so we would call that the magnitude of a certain vector. All right, so we'll just write down here, right? So velocity, speed, distance, all of these words are referring to the length of this vector or the magnitude of this vector. All right, so those are common words that you'll see kind of pop up. All right, the other thing that we had, so we talked about the segment part of the definition. All right, the other part of the definition that we have is directed. All right, directed is the angle part, right? So if you have a direction, right, that means you're going some sort of way. So you need an angle. All right, so because we have a direction, so the direction, right, we're going to use theta because why not? We've been using theta the entire time. All right, that's going to tell us in what direction that our vector is traveling. All right, so direction is theta. All right, and this tells us what direction our vector is traveling. Okay, so it's a directed line segment. So direction is the angle at which we are traveling, and it's a segment, so we know that it can be measured and it has length. Right, and we call that length the magnitude. Other words that would describe this, so if we were doing a word problem, would be like velocity, speed, distance. Those are all talking about your length of your vector or your magnitude. Okay, so those are kind of your basic vocab words, and that's what a vector is. All right, so directed line segment, a line segment that has both length and direction. Cool. All right, now for labeling vectors, there are three different ways you can label, three main ways. I'm sure there are probably other ones. I've only ever seen three ways, all right, to label vectors, and they look like this. All right, so first off, vectors, right? So we have our XY axis, XY. Cool, nothing new. We've been having XY axes the entire time. All right. So a vector would look like this. Kind of looks like a ray that you had in geometry. But I will remind you, a ray has an endpoint, but continues infinitely in the other direction. All right, so this is not a ray. This is a vector, even though I know they look exactly the same. All right, so just like with rays that you learned about in geometry, one conventional way to name them is using their, what we call the initial or the starting point. So initial or starting point, and the terminal point, so the ending point. So right here we would call B the terminal point. Terminal. Cool. All right, so technique number one for naming, all right, is to use the initial. So use initial and terminal, uppercase letters. So for example, we could call this one AB. and we would use a one directional arrow over top of the two letters. So yes, this is the exact same naming convention that rays use, but it is not a ray, it's a vector. We're not in geometry. That's how we know. So you're probably wondering, how would I know? We don't do rays in this class. That's geometry. Yes, we're not learning about the sun. We don't have rays. Okay, so second technique. All right, so second naming technique would be to use a bold lowercase letter. All right, and generally they're going to put those somewhere in the middle of the vector itself. So it's kind of hard to do bold letters when you're writing, right? You have to like make them bold. But when you're typing, it is much easier. All right. So the second naming convention would be to use a bold. We'll just like bold that out, right? Bold. Cool. More cool. Bold lowercase letter. All right, and there are some typical ones that are used. So you see over there, that's a U. That is a very common vector letter to use. So for example, right, we have vector U. Other common letters are going to be V, W. They tend to stay towards the end of the alphabet with vectors. I'm not really sure why, but V and W are big ones that you'll see. It doesn't matter though. It could be any letter you want. It just has to be bold and lowercase. But like I said, the most common letters you're going to see are U, V, and W. All right. The third and last method is what we call component form. And this is the most commonly used technique. The bold, so I will say the bold lowercase letters are probably the second most commonly used one. No one ever uses the first one, but it's the first one that you're going to see in here. And we do talk about the initial and the terminal points. We'll talk about them next class. But naming a vector using the uppercase letters is definitely the least used technique. Most of the time you're going to see the bold lowercase letter is very common. And then most of the time when you have vectors, they are in this component form. And we're going to talk about what that is right now so that it makes sense. So component form is when your initial point is at 0, 0, like we have drawn in our picture. We have the 0, 0 is where our starting point is. All right, so initial point is at 0, 0. And your terminal point, that's your ending point, right, is at x comma y. And something to pay attention to is we didn't use parentheses here. These are what we call angled brackets, right? They're not the less than or equal to signs. They're angled brackets. All right, so they're not the same as the less than or equal to sign, right? They're just pointy parentheses. Pointy parentheses, that's what they are. All right, and so if you see these pointy parentheses, that's telling you that this is a vector and it's in component form, meaning the letters that you're given, or sorry, the letters, I'm looking at X and Y, so that's why I call them letters. They're usually numbers, right? So the numbers you're given in that angled parentheses, those are your terminal points, and it's known that if it's in this format that your starting point or your initial point is at 0, 0. So for our example vector over here, like in the picture, all right, we see that A is at 0, 0, so that means our initial point is at 0, 0. So whatever coordinate we had for B, it's some x comma y. We don't know what it is. It could be 4 or 7, could be a million, comma 2 million. It doesn't matter. All right, it's some x comma y value. All right, so wherever b is, since a was at 0, 0, if we put the angled, that's not an angle, angle, if we put the angled brackets around it, then that would indicate that our terminal point is whatever that xy value is, and our initial point had to be at 0, 0. So this is component form, and we're going to talk a lot more about component form next class in our next video, because we're going to talk about how do you get something into component form, because any vector, it could be floating in the third quadrant, we can transform it into this component form. And the reason why we do that is because it makes it really nice to have everything right at 0, 0. It's going to make adding vectors easier. It's going to make multiplying them easier. It's going to make setting up a word problem so much easier if everything just kind of starts right at 0, 0. So we're going to talk more about how to get something into that component form next class. This class, we're really just going to be using the component form to figure out the next two things we're going to talk about, which is magnitude and direction. All right, so, boop. All right. Come on. Oh, I'm trying to scroll on the wrong thingy. Miss Leslie, what you doing, girl? What you doing? You crazy. You are crazy. Okay, so magnitude. We've already talked about this, but we're going to touch on it a little bit more. Magnitude is the length of your vector. All right, so this is our length of a vector. All right, and the symbol for magnitude is a little funky looking, but it's nothing super crazy. The symbol is like a double absolute value sign. So you have like double on the outside, and usually what goes inside is whatever you're naming your vector. So for instance, we could say like lowercase bold u. So this would say, this represents magnitude of vector u. So however you're naming it, sometimes you're going to see component form inside the magnitude symbol, and that indicates what is the magnitude of this component form vector. You could see the uppercase letters inside that, the little double absolute value. Just the double absolute value itself, that's the symbol. And then inside you're going to put whatever vector it is that you want to find the magnitude of. Now, to find the magnitude, it's actually really easy. You've done this before. It's length of something. Well, you've done that before. You've found the length of something, I would hope so, of a segment like on the XY axis. It's called the distance formula. You've all heard of the distance formula. So one technique for finding magnitude is to use the distance formula, which I'm sure you all forgot. I taught geometry for 5 years, and we use the distance formula all the time. The kids never remember it. I just honestly don't even know how you forget it. It's one of the easier formulas. So distance equals the square root of x1 minus x2 squared plus y1 minus y2 squared. That's a distance formula. Now, another way to do, so you take your x, subtract your other x, you square it. You take your y, you subtract your other y, you square it. And then you take the square root of the whole thing. Easy, easy peasy. But there's another technique. So if you don't like doing that, you can also use the Pythagorean theorem. So second technique is to use the Pythagorean All right, so because it's the distance formula. So I know we have like c squared equals a squared plus b squared or whatever, but if you square root c, it becomes the square root of a squared plus b squared. Literally, like, look, they're like the same thing. A just represents the length of that side of the triangle, so you're having to like You would count, obviously. You wouldn't like subtract, but you're subtracting in essence. Like if you don't have a picture, you're subtracting the distance from here to here to find the length of that side. Same thing across the bottom. So you're essentially you're doing the exact same thing with the distance formula as you are with the Pythagorean theorem, but because counting is easier than subtraction, people like using Pythagorean theorem better. But what it does mean is that you have to always sketch it out if you're doing Pythagorean theorem, which to each his own, right? Some people just think that that's easier, but I mean, that's okay. It's whatever you're into. You're doing the same math. All right, last piece is direction. All right, so your direction, right? We know that this is the angle that our vector is making with that x-axis. All right, so this is the angle our vector makes with the x-axis. It's basically our reference angle, right? So it's the angle between like our vector itself and the x-axis. So it's like a reference angle, right? So you can always think of this like it's the reference angle because we've talked about that a lot. Okay, so if we have like a little picture, you know I like pictures. We'll draw it. I know there's no L in draw, but like I just feel like it should be there, so I say draw. But whatever. Okay, so here's our vector. Cool. This theta is our direction, right? It's that angle right there. It's our reference angle. All right, and how we're going to find that is we're going to drop it down. We're going to draw across, make ourselves a little right triangle. All right, so whatever this point is, right, it's going to be some x comma y, our terminal point right there. So this is our x value, this is our y value. If we want to know what theta is, wouldn't we just do the tangent of theta, right? Because we have opposite is going to be the y value, adjacent is going to be x. When we're given it in component form, we know both the x and the y. So what we're going to do is we're just going to set up for tangent. Tangent theta equals opposite over adjacent. If we want to get theta by itself, inverse tangent. So theta equals inverse tangent of y divided by x. Cool. Okay, that is it. That's the math we're doing. We're doing Pythagorean theorem and inverse tangent. That's the math. It's not that bad. All right, so we're going to do our two examples. We're going to find the magnitude and direction of each of the following component form vectors. And then we're done for today. All right, which is probably good because we're at 23 minutes right now. Okay, so here we go. I always recommend sketching it, and on your homework, you have to sketch it. I made you. All right, so hold on, I scrolled on my own paper, but I didn't scroll on here, so there we go. All right, 3, 5. So 3, 5. All right, I put my initial point at 0, 0 because this vector is in component form because I have my angle brackets. So I know that my starting point is 0, 0. My ending point is 3, 5. All right, so I'm going to make myself a little triangle. All right, I know this side is 3. I know this side is 5. Boop, boop, 3, 5. Excellent. All right, so magnitude. All right, so this is vector u. My magnitude of u is the length of my hypotenuse. Pythagorean theorem. So to find magnitude of u, it's 3, the square root of 3 squared plus 5 squared. Right? So 3 squared is 9. 5 squared, 25. I should have went down. I knew I should have went down, and then I didn't. And then I regretted it. It's okay. I moved it down now. There we go. All right, so 9 plus 25 is 34. don't think we can simplify that. 34, 17 times 2. 17's prime, 2's prime. So no, that's as simplified as we can get it. So our magnitude is the square root of 34. All right, theta is going to be inverse tangent of y over x. All right, so I'll go to my trusty calculator. Second tangent of opposite divided by adjacent, enter, and I got 59 degrees. Guess what? That's it. You're done. All right, magnitude, square root of 34, and theta, 59 degrees. That's it. That's all there is to it. Okay, so let's do the second one. Now this one's going to be a little bit more complicated, only because our angle is not in the first quadrant, but we're going to talk about it, and it's an easy step. Okay, so here we are. Oh, we should probably put this somewhere different. There we go. All right, so -7, -4, that is quadrant 3. So I'm going to go ahead, I'm going to draw my third quadrant vector. So we have -7, -4. We are going to draw a perpendicular and we're going to draw over. So here's our little bitty triangle. All right, so let's go ahead and find our magnitude first. So this is vector u. So I want to find, so we know our length, or sorry, this is a v, not v. I think I just called it a u. That's wild. All right, so magnitude of v. That's our length of our vector here. All right, so we're going to do Pythagorean theorem. All right, so square root -7 squared plus -4 squared. Remember, when you're putting this into your calculator, you want to put parentheses around those negative numbers. All right, so we've got -7 squared plus 4 squared is 65. So this is the square root of 65. Can that break down anymore? Nope, it's 5 times 13. Both of those are prime numbers. So that's the answer for our magnitude. It's just square root of 65, right? For theta, all right, same deal. So inverse tangent of opposite. So x is -7, y is -4. So -4 over -7. So theta is going to give us second tangent, -4 divided by -7. Enter. 30. 29.7. So 30 degrees. Now, you know as well as I know that this angle in the third quadrant is not 30 degrees, right? The vector is not traveling 30 degrees. 30 degrees is in the first quadrant. What it's giving us is this measure right here, right? That reference angle. So if we want to actually find the real direction, we have to kind of do some addition, right? Because we want to know that we're actually traveling this direction, not 30 degrees, because that's not right, right? So we need to figure out this angle. That's the actual direction of our vector. All right, well, we know that from here to here, it's 180, because we know that. All right, and now we know that from here to here is 30 degrees. Guess what we're going to do? We're going to add them together. So our actual direction is going to equal 30 plus 180, which is 210. So our actual direction of our angle is going to be 210 degrees. And that is our final answer for that one. All right, so magnitude, square root of 65, and the direction, 210. So when you have a vector that's not in the first quadrant, you got to do a little bit of math to find your actual angle, right? It's always going to give you that reference angle, and sometimes it's going to give you a negative number, but it's still just the reference angle. So when you do your inverse tangent, just be mindful that that's what it's giving you. All right, well, that is it for today's video. Hope you guys enjoyed it. Work on your classwork, and that's it for today.